All right, we're going to take a look at solving polynomial and rational inequalities. Start off with some polynomial inequalities. All right, so I've broken it down into 4 steps. All right, with that said, the first step is we want to find the related equation. So we're going to replace the inequality symbol, whether it be less than, greater than, less than equal to, greater than equal to, with an equal sign, and we're going to solve it. And the solutions that we find are critical values, all right, for this polynomial inequality. And these critical values represent the zeros of the given polynomial. So we're going to find the solutions of the zeros of the polynomial. So if we can factor it down to its linear factorization, we'll be able to see the zeros, we'll be able to see the critical values that are formed. All right, with these critical values, they're going to set up our possible solution set intervals. So we're going to use these values to determine the interval solutions. So we'll set up our x line, all right, and we'll determine, and we're solving for x. And we'll determine what intervals are formed based off the zeros of the polynomial. And we'll choose an appropriate test value to evaluate and see if it satisfies it. So again, we're going to look at solving a polynomial inequality algebraically. So again, if you graph these polynomials, you're going to see the zeros, which again are the x-intercept locations. They break up your inequality into different regions, and we got to see if we're less than or greater than. And if we have the graph in front of us, we can see it looking at it. So maybe we can look at it also graphically and show you. But let's go ahead and solve this quadratic inequality. So here in example A, we have 2x squared plus 5x greater than 12. With that said, the first step, let's go ahead and look at step 1. Let's solve the related equation. All right, so what we're going to do is drop the equal sign, drop the greater than symbol and put an equal sign. So that implies 2x squared plus 5x equals 12. There's the related equation. All right, and as we're solving that, we're going to solve by trying to factor, right? We're going to set it equal to 0. It's a quadratic equation. We know quadratics can have up to 2 real number solutions, and that's what we're looking for, these real number values. They're our critical values for solving our polynomial inequalities. And with that said, this is a quadratic where we can solve easily by factoring. So as we're solving this one, I'm going to go ahead and factor into its 2 linear factors. Every quadratic has 2 linear factors, and we can see this one using nice rational numbers. We know with 2x squared, we'll need a 2x and an x up front to make the 2x squared product. We multiply the 2 linear factors together. We know our goal is to look at our constant term and find a factor combination like 1 and 12, like 2 and 6, like 3 and 4. Well, 3 and 4, we can work with those 2 numbers. If we were to put a 4 here on the outside, and we were to put a 3 here on the inside, right, those are the 2 factors of 12 I'm going to use. You'll notice that our outer product, right, let's check our factoring, they multiply together to give us 8x, and our inner product multiplies to get 3x. Well, we can get a 5x back from that. We know 8x minus 3x makes 5x. That's our goal, to get that middle term coefficient. So we're going to need a plus with the 4. We're going to need a minus with the 3. Right? If we were to distribute or fold that out, we're going to get 2x squared plus 5x minus 12 back. So at this point, we have our linear factorization. So we can go ahead and state our zeros. And again, we can use the zero factor property and show that algebraically. Set each factor equal to 0, and we'll solve for x. And as we do that, we get x equal to 3 halves. And over here, as we solve for x, we get x equal to negative 4. So again, we've got 2 critical values. All right, so that's our key part, is finding these critical values. So let's write those up here. And the critical values in a polynomial inequality is the solutions, the zeros to your polynomial related equation. So we got negative 4 and 3 halves. So what we're going to do is we're going to take those 2 numbers. All right, and we're going to go ahead and build in the x line. Here's all real numbers x. And let's place these 2 critical values on here. So we have negative 4, and we have 3 halves, or 1 1/2, or 1.5, me over here. All right, so there's our x line. Now, as we look at that, again, these are our zeros. Now, one thing we want to keep in mind is that the inequality we're looking at is greater than 12. So since we don't have equality, we're not going to be using -4 and 3/2 as our solutions, because those would make it equal 12, right? Those are solutions to our late equation. So I'll put a little open circle on that. Now, as we look at the different possibilities of solutions, the different intervals, so let's set up, right, our test intervals. So that'll be our next step. Let's find these test intervals for our solution set. So we have -infinity to -4. So all x values less than 4. Now again, we can't use -4 because it's just a greater than problem, not greater than or equal to. We know -4 makes it equal 12. That's a possibility for solutions. We also have to look at the numbers that are greater than -4, right, and less than 3/2. Those are possibilities. Numbers like -3 and -2 and 1. And then, of course, we have the possibilities of 3/2 to infinity, all the numbers greater than 1.5, like 2, 3, 4, 5, all the way to infinity. So those are our test intervals. Now we want to pick a test value. So now we want to figure out if -infinity, -4 is in the solution set. Well, the only way to figure that out is to pick a number in that interval and see if it works. If it works, then yes, that's part of the solution set. We only need one number to test it. If one number works, they all work. If it doesn't work, none of them are going to work. So let's pick an easy number to work with, and let's pick an integer value like -5, right? Be an easy one. That's a number less than -4. So I'm going to test for -5. And anytime I can use 0, I'm going to go ahead and look at this middle interval. What's a number between -4 and 3/2? Easy number, we can plug 0 in. And we'll use the smallest whole number possible here. We can use a 2. 2 is greater than 3/2. So I'm going to test with 2 on that one. So let's see if these are part of the solution set. So as we go in here, let's plug it in. So it's -5 in solution set. Now again, what are we solving? It's quadratic inequality. So with our quadratic inequality, right, we're given 2x squared plus 5x. We want to know if it's greater than 12. So let's see if it is. So again, picking that test value of -5. So we got 2 times -5 squared plus 5 times -5. And our question again is it greater than 12. So as we simplify that, well, what do we get when we simplify? Right, we know that -5 squared is 25, right? 2 times 25 here, plus 5 times -5, which is -25. And is it greater than 12? Well, we got 50. 50 minus 25. 50 minus 25 is 25. 25 is greater than 12. It works. So all x values less than -4, they're in the solution set. So it satisfies that polynomial. That's a solution, right, to this polynomial inequality. Now, what happens for the numbers that are greater than -4, right, and less than 3/2? Let's test that interval that we formed. So let's do its work right here beside it. And again, our test value is 0. So it's 2 times 0 squared plus 5 times 0. Is that greater than 12? Well, it simplifies quickly. 2 times 0 squared, 0. 5 times 0 is 0. 0 is not greater than 12. 0 is less than 12. Didn't work. So that means every number in that interval does not work. And then our last check, let's go to our last interval. So let's check with 2. So let's test with 2. So again, our test number is 2, and we're testing the interval of 3/2 to infinity. Well, does that work? So as we plug that in, that's 2 times 2 squared plus 5 times 2. Question, is it greater than 12? Well, 2 times 2 squared, that's 2 times 4 plus 10, greater than 12. That's 8 plus 10, greater than 12, which is 18, right? Greater than 12. True, 18 is greater than 12. So it works. So we need to include that interval in the solution set. So we've solved our polynomial inequality. Let's write our solution set over here. So our solution set, all x values less than -4, -infinity, -4 the parentheses, or all x values greater than 3/2. So there's our solution set to this quadratic inequality. Again, solving using the critical values, which are, again, the zeros of the polynomial, the zeros of the related equation, the solutions. So again, I want to be able to solve, and solve by factoring, since we've been factoring polynomials.